Okay, last group from Grace Hopper is a group called Node Lego. Data structures are a big part of our curriculum here at Full Stack and at Grace Hopper, something we introduce in the first couple days of the program and then revisit again and again and again. And this group decided to create an easy-to-use tool for students to visualize different types of data structures as they build them step by step. It was a big challenge, and I thought that they did a great job with it. Here is Node Lego.
Thanks, Emily. Hi, my name is Julia, and with my colleagues Carol, Karina, Grace, and we created Node Lego. Node Lego is a tool that allows software developers and computer science students to visualize data structures, including binary search trees, linked lists, stacks, and queues. This was inspired by our studies at Grace Hopper. As new students, we were introduced to a variety of data structures and found that the best way to understand them was to see visual models. So our sort of conceived notion of this project was as a fun way for users to interact with virtual nodes and play around with them to create data structures of their own. And now Carol will walk you through some of these visualizations in action.
On the client side, users are able to add and remove nodes seamlessly through the click of a button. They are also able to peek at the head nodes of the queue and stack data structures. In order to create these visualizations for our users, we needed to create these data structures behind the scenes. By using a series of helper functions, we recreated instances of linked lists and binary search trees. In order to manipulate particular nodes in our linked lists, queues, and stacks, we converted our linked list class into an ordered array, thus allowing users to search for nodes at particular indices. With a search function in place, we were able to create accompanying methods for insertion and removal of nodes at particular indices. Our site also allows users to upload saved CSV files and display them as the data structure of their choice. In this example, Omri has saved or has uploaded a CSV file containing a list of values, and it's automatically converted into a linked list. We do this through using React File Reader. Finally, another feature of our project is that the time complexity of adding and removing nodes is displayed with each operation, thus keeping users aware of the cost of their operations. And now Karina will talk to you about our binary search tree features.
Our goal was to create a mutable tree that would re-render as the user adds and deletes a node. To accomplish this, we started out with a tree class object that has a parent and child relationship. This relationship is saved on our Redux store so that we can recreate the tree on the front end. When we're removing a node, we deleted all the references to the node so that the system understands that the space is freed. We utilized this Node.js built-in garbage collection to take care of the potential leak problem. The data transformation into visuals is happening in the back, where we're managing the virtual DOM. First, JavaScript compiles the data, then we save a copy of the data structure on our Redux store that we feed into our utilities functions that generate the JSX elements with SVG. Our binary search tree type page, we apply D3 animation to our virtual DOM again. What we do is we use the node value to calculate the transition time so that we are highlighting our virtual DOM in the order of tree traversal: pre-order, in-order, post-order, and breadth first. Now I'll pass it on to my colleague Grace, who will demonstrate how we allow users to save their data structures.
So since this is a learning and development tool for developers, we wanted to allow users to create instances of data structures that they could view later. And saving these instances that users had created in the browser did pose a challenge, since the objects we were working with were so deeply nested that they couldn't be converted to either JSON or JSON-B without circular references. And we were essentially faced with one of two choices: either use a more complex relational table model to save individual nodes and chart their relationship to other nodes, or save an entire single data structure. And we chose the latter, using a modified heap-to-array algorithm to save an entire data structure as a one-dimensional array of objects. And in this way, parent, child, previous, and next object pointers could be transformed into indices in the array. In this way, we're also able to save both incomplete and complete data structures as arrays of JSON in Postgres. When that information is reloaded, we feed it to the original component, which renders it. And now my colleague Julia will finish off with some final remarks.
Throughout the course of our project, we learned a tremendous amount about representing and manipulating data to serve different purposes for the back end and front end. We were able to take raw data and then transform this single source of truth into modified iterations for our various use cases. Thank you very much. We hope that our project has inspired you to learn more about data structures, and please visit our website, nodelego.tech, to create some of your own. Thank you.
It's so critical when you're learning data structures to be able to visualize what happens when you add a node, remove a node, when they rebalance. So I think this app is actually it'll be very useful to future developers. I think it's really well done.